Welcome back. In this video, we're going to treat the force as a vector, which it is, and solve for the x and y components of the vector. In the problem you see in front of you, there are two charges. Now previously we did some problems with two charges. We said let's just find the magnitude of the force. So let's start a similar way. There are two charges. We'll let this uppercase Q that's in the center have a value of, let's say, let's make it a negative charge, minus 9.00 microcoulomb. That's the force in the center, that capital Q. The other one, the smaller q over here, let's give that a value of a plus 2.20 microcoulomb. Two charges. Now, what about the distance between them? Well, here, let's imagine some separation like that. We'll call it R. For the separation R, let's use a value R equals 55 centimeter. Now, let's go ahead and convert this thing to meter, because that's going to be the correct unit to use in the equation. So that's going to be 55 times 10 centi minus 2 meter. So this is going to be 0.550 meter for value of R. 55 centimeters, 55 to minus 2.55 meter. Now, let's start by calculating. We want to get the components of the force. For the two charges, let's start by finding the magnitude of the force that exists between those two charges. So we use the formula for electric force. F sub B equals K sub B. This is Q1, Q2 over R squared. In this case, Q1 is going to be the large Q, Q2, the small q, over R squared. Okay, let's plug in the values. K sub B, that Coulomb constant, 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Coulomb constant. The first Q, the large one, minus 9 microcoulomb. Micro is 10 to the minus 6 coulomb. The second charge, a positive 2.2 microcoulomb. Again, microcoulomb to the minus 6 coulomb. The separation squared, we're going to use the value in meters. 55 centimeter, 55 to the minus 2, 0.55 meter. Quantity squared. Okay, now to solve this problem, you could go directly to the calculator. I find it tedious to have to type in all those powers of 10. I prefer to gather up the numbers, gather the powers of 10, and solve that. Okay, so here are the numbers. start from left to right, 8.99. There's a -9. There's the 2.2. We're going to have a 0.55 squared in the denominator. Just to remind you of the units, we have, this is meter squared, cancels meter squared. Coulomb times coulomb cancels coulomb squared. The answer will be newtons. Okay, now for the powers of 10. There's a 10 to the 9. Microcoulomb, microcoulomb, we have 2, 10 to the -6. Already converted the centimeter, so we don't have a power of 10 in the denominator. Unit will be Newton. Okay, now the first part I think is more straightforward. Put that into the calculator. 8.99 times -9 times 2.2 divided by 0.55 squared, or divided by 0.55 twice. You'll find minus 588. Now over here, the powers of 10, you see you have 10 to the 9, -6, -6, 10 minus 12. So 9 minus 12, 10 minus 3. So the number we would get for this thing, that's minus 588 times the -3, will be minus 0.588 Newton. Now we want the magnitude. Let's come back. Let's put these vertical bars. Magnitude of this thing is going to be the positive number 0.588 Newton. Now these charges, we have a negative and a positive, so we know this is going to be an attractive force. That's the magnitude. But we want to find the force components, the x and y components of the vector. So let's first remember, when you have a pair of charges, you'll always have two forces, equal and opposite. This large Q is attracted to the upper right. This red one is attracted to the lower left. Now it's a little bit crowded there. Let me try to clean it up some. The point being that the force with which the large Q is attracted to the small q and the small q to the, those forces are equal and opposite. Equal and opposite in direction. Both of those forces will have a magnitude, length of the vector, 0.588 Newton. But one goes to the upper right, one goes to the lower left. So they're equal, magnitude, opposite in direction. All right. So there are two forces, but we don't need to solve for every detail of the two forces because they're going to be equal and opposite. Let's solve for, let's state what it is we want. We want to know, let me say come over here, the force components on Q. The force components on Q. So we're not trying, we don't need to solve for, well, you can solve for either one. The force acting on this capital Q or the force acting on the lowercase q. We want the force components on Q. We know that this force, or this charge, is attracted to the big one, like that. So the force components, if we decompose this thing, let me open this up, make it bigger here, clean it up a little. This thing is attracted downward like that. So let's just call that force vector on Q. That's the force on this small, there's a big Q and a little q. It's the force on the small q. Now we're going to break that into two components. This vector, any vector can be decomposed into two perpendicular components. This one, we have a y component that looks like that. X component, let me draw a little straighter. The X component like that, fx. Okay. To solve this thing, we're going to have to do some trigonometry. So we'll have to specify an angle. Let's put this angle right here, theta. Go ahead and open it up again. There we go. So there's the force. I'll go ahead and put an E and a 1. It's the electric force. Well, actually, that's not 1. Just a little q. The force acting on this q. There'll be an opposite force acting on the capital Q. They're the two components, fx, fy. The trigonometry is such that fy, the side opposite to the hypotenuse, this force F sub q, let me write that bigger. The force that's acting on this q is the hypotenuse of a right triangle. So Fy is going to be the magnitude of that force times sine theta. Fx, let me move this down some. The magnitude of that force, that's the hypotenuse, cosine theta, except we have not specified the signs. Notice that Fy is pointing down. That will be a negative component. Notice that Fx points to the left. That will be a negative component. So we use the trigonometry. The side opposite the angle, F sub y, right, a little neater, will be the hypotenuse times sine theta. The side adjacent to the angle, the hypotenuse of the triangle times cosine theta. But we have to take into account the direction of the vectors. Fy points down, we give it a negative sign. Fx points to the left, we give it a negative sign. Now let's go ahead and solve the problem. What I've drawn here is FQ with the bars. That's the, at this point, I don't have to call it F sub Q because that hypotenuse will be the same for either vector. Fe, Fe. What I've drawn there with the arrow, this right here, this FQ, this thing, let me highlight in red. Okay, that vector is the force acting on that Q with the red circle. The magnitude of that vector is going to be what we already calculated, Fe right here with a double bar. So we can put that into the equation here. Now let's just go ahead and solve the problem for completeness. So for this problem, the x component points to the left minus this magnitude of the vector, 0.588 Newton, times cosine theta. Well, we haven't specified theta yet. Let's give theta a value (36°). 36 degree. Okay, so the x component we will find is a minus 0.476 Newton. The y component, from the y component for the force on that charge is pointing down, negative times the magnitude of the vector, 0.588 Newton. Y component, sine of the vector, sine of the angle, y component equals minus 0.346 Newton. Okay. That is a problem that illustrates how to get the components of the vector, because force is a vector, has a magnitude, has direction. The magnitude we get from the equation. We simply take the positive, we get 0.588 Newton. The components, we have to use some trigonometry. We have to have a picture of how this thing is oriented. We need to specify which charge are we talking about. Are we talking about the force on that large capital Q, or the force on the smaller one in red, that lowercase? Okay. So let's, and then the trigonometry, once you know the angle, for the y component, sine of the angle, the x component, cosine of the angle times hypotenuse, you have to look at the picture, decide what's positive, what's negative, which way do those vectors point. Let's illustrate another example. The numbers will be the same, but the signs will be different. Suppose you did the equation, you solved the magnitude of the vector, and you found out the magnitude of the force, 0.588 Newton. Then you looked at the picture, and the picture looked like this. And once again, I said the force components I don't know why that's doing that. Force components that are really acting on Q, this lowercase q. Well, now go ahead and expand this thing out. The force acting on this, remember this is the negative, this is the positive. is going to be attracted. So there's the force. What's it? The force Q. The y component of y is there. The x component is there. Once again, we put the angle in the triangle. Now we find this x component points to the right. That is the positive direction. Pointing to the right, that's the positive direction. The y component is pointing up. That's the positive direction. So if we say same charges, the same separation r, the same theta, but it's a new picture or a new quadrant. Right. This is the first quadrant, the second, the third, the fourth quadrant. So it's a new quadrant. So now what we would find, the numbers would be the same, but the signs would be different. So for this problem, clean this up. Same charges, same r, same theta. But now we would find fx instead of negative 0.476. Now it's too small. We would find with this problem fx is plus 0.476 Newton. It's going to the right. Fy, which is pointing up, is now plus 0.346. Okay, once again, let's think about the steps. When you have the two charges, the separation, you can solve the equation, get the magnitude of the force. Then you ask, well, there are two forces, one on each charge. Which charge am I specifying? Depending upon whether they're attractive, repulsive, you figure out the direction of that vector. You look at the picture, you look at the angle, use the trigonometry. Sine theta times hypotenuse for the y component, cosine theta times hypotenuse for the x component, but the plus, minus sign depend upon the picture. One more example just to illustrate. What if it looks like this? This picture here. Once again, negative charge, positive charge. Now, I could give you a problem with two negative, two positive, but this is to illustrate. So once again, there's the attractive force acting on Q. The components of this thing, I can draw it like this. There's the Fx. There's the Fy. Now what about the angle? Well, let me clean it up a little bit. Well, here's the angle, theta. It'll be the same as angle theta. Or if you prefer, can draw it differently just for clarity. There's Fy, there's Fx, because it's attractive. because it's attractive. Once again, we'll say same charges, same r, same theta, but it's a new picture. So the numbers will be the same. What about the sign plus minus? The fx, notice the x component points to the left. That's the negative direction. So we would say fx equals, it's going to be negative, oh, some room there, negative 0.476 Newton, because it goes to the left, negative direction. The y component, so your picture, y component points up. That means the y component is going to be positive 0.346. Okay, so just to repeat, when you have the charges, the separation, you solve, use the equation, find the magnitude of the force. But to get the vector components, you need to look at the picture. Which charge am I solving for? Is it attractive? Is it repulsive? The direction of the vector. You draw the vector, draw the components, do the trigonometry with the sine and the cosine, and assign what is positive, what is negative. Okay, I think that's enough. So I thank you once again for listening all the way to the end.